We are back with a new section, Deterministic Dynamical Systems. Here we will simulate mathematical models that represent how our data was generated. Let's move on to the first video of this section that deals with plotting the bifurcation diagram of a chaotic dynamical system. There are four types of deterministic dynamical systems we will consider here: are discrete time dynamical systems, which are iterated functions, cellular automata, ordinary differential equations, and partial differential equations. A chaotic dynamical system is highly sensitive to initial conditions. Small perturbations at any given time yield completely different trajectories. The trajectories of a chaotic system tend to have complex and unpredictable behaviors. Many real-world phenomena are chaotic, particularly those that involve nonlinear interactions among many agents, complex systems. Examples can be found in meteorology, economics, biology, and other disciplines. In this video, we will simulate a famous chaotic system, the Logistic Map. This is an archetypal example of how chaos can arise from a very simple nonlinear equation. The Logistic Map models the evolution of a population, taking into account both reproduction and density-dependent mortality, starvation. We will draw the system's bifurcation diagram, which shows the possible long-term behaviors like equilibria, fixed points, periodic orbits, and chaotic trajectories as a function of the system's parameter. We'll also compute an approximation of the system's Lyapunov exponent, characterizing the model's sensitivity to initial conditions. Now let's start by importing NumPy and matplotlib. Next, we'll define the logistic function, which equals the product of r, x, and 1 minus x. And here is the implementation of this function in Python. Define logistic r, x. Also, we return r into x into 1 minus x. Why don't we see a graphic representation of this function? Let's execute this code. Now you can easily visualize how our logistic function looks like. Our discrete dynamical system is defined by the recursive application of the logistic function, as shown in this expression. Let's simulate a few iterations of this system with two different values of, using this code. Let's run this. On the left panel, we can see that our system converges to the intersection point of the curve and the diagonal line or fixed point. On the right panel, however, using a different value for r, we observe a seemingly chaotic behavior of the system. Now we simulate this system for 1000 values of linearly spaced between 2.5 and 4.5, and vectorize the simulation with NumPy by considering a vector of independent systems, one dynamical system per parameter value. So in the next cell, continue writing n equals 10,000 and r equals np.line space 2.5, 4.5 and n. Then we use 1000 iterations of the logistic map and keep the last 100 iterations to display the bifurcation diagram. Also, we initialize our system with the same initial condition, x0 equals 0.00001. For this, declare x as 1 e minus 5 into np.ones and pass n to this function. We also compute an approximation of the Lyapunov exponent for every value of r. The Lyapunov exponent is defined by this expression. We first initialize the Lyapunov vector. Lyapunov equals np.zeros with n. Now we simulate the system and plot the bifurcation diagram with this block of code. The simulation only involves the iterative evaluation of the logistic function on our vector x. Then, to display the bifurcation diagram, we draw 1 pixel per point during the last 100 iterations. Let's execute this code. The bifurcation diagram brings out the existence of a fixed point for r less than 3, then 2 and 4 equilibria, and a chaotic behavior when belongs to certain areas of the parameter space. We observe an important property of the Lyapunov exponent. It is positive when the system is chaotic, in red as you can see in this diagram. Great!